of switch. Here our main objective is to design a clap on and clap off switch circuit. Here the components we used in the circuit are condenser mic, 555 timer IC, transistor BC547, resistors, those are 1K, 47K, 100K ohms, and one capacitor 10 microfarads. Here the electronic condenser mic for sensing the sound. And one more important component is D flip-flop.
Here we are using electric condenser mic for sensing the sound, transistor to trigger the 555 timer IC, 555 IC to set and reset the D flip-flop, and D-type flip-flop to remember the logic level, LED on or off until next clap or sound.
In the designing of clap-on clap-off circuit, we are using the main components such as NPN transistor, 555 IC, and a D flip-flop with a condenser mic. The circuit is acting like a switch, and the 555 IC is acting in a monostable multi-vibrator. Here we are using a D flip-flop, that is positive edge triggered clock is applied to the D flip-flop. Transistor base is connected to the positive end of the condenser mic, and the negative end of the condenser mic is connected to the negative potential, that is ground. And the base is also connected to the VCC through a 47K ohm resistor. The collector terminal of the transistor is connected to the VCC potential through a 1K resistor. The emitter of the transistor is connected to the ground potential. The output from the collector of the NPN transistor is connected to the second pin of the 555 IC, and the first pin of the 555 IC is connected to the ground potential. The fourth pin and the 8th pin of the 555 IC timer is connected to the VCC potential. The 7th pin of the 555 IC is connected to the VCC potential by using a 100K ohm resistor. 7th pin and 6th pin are shorted by a connecting wire simply, and the 6th pin is connected to the ground through a capacitor of 10 microfarads. The output from the 555 IC is taken from the 3rd pin of the 3rd pin and applied to the 3rd pin of the D flip-flop. Here we are using the D flip-flop of 14 pins, and the 2nd pin and the 6th pin of the D flip-flop is shorted by a connecting wire. The 1st pin and 4th pin are shorted and connected to the VCC potential. The 5th pin of the D flip-flop is connected to the ground through a LED. As it is common to every IC, the 7th pin of the D flip-flop is connected to the ground, and 8th pin of the D flip-flop is connected to the VCC. 14th pin of the D flip-flop is connected to the VCC potential. The battery positive terminal is connected to the VCC potential, and negative terminal is connected to the ground.
Initially the transistor is in off state because there is not enough base emitter for voltage is turned off. Point A is at high potential, and the point A is connected to the trigger pin 2 of the 555 IC timer, and a result trigger pin 2 is also at high potential. The trigger the 555 IC timer through a trigger pin 2, and the voltage of the pin 2 is must be below VCC by 3. So at this case, no output at output pin 3 means no clock was applied to D-type flip-flop, that is IC 7474. Thereby no response from D-type flip-flop, and so LED is off. Now when we produce some sound near the condenser mic, this sound will be converted into electrical energy by using a condenser mic, and it will be the potential at base which will turn the transistor on. As soon as the transistor becomes on, the potential at point A would become slow, and it will trigger 555 IC timer because of the low voltage at trigger pin 2. So the output pin 3 will be high, and a potential clock pulse will be applied to the D-type flip-flop, which makes flip-flop to respond. The LED will turn on.
This set state of flip-flop will remain as until next clock pulse. The detailed working of D flip-flop has been glow. As soon as this transistor becomes on, the potential at a point A would become low, and it will be trigger the 555 IC because of a low voltage at a trigger pin 2. So output pin 3 will be high, and positive clock pulse will be applied to D flip-flop, which makes the flip-flop respond and LED will be turned on. This state of a flip-flop will remain as a until the next clock pulse or next clap. Here we are using a 555 IC in a monostable mode whose has been used a clock pulse for a D flip-flop. So the clock pulse will be high for a few seconds and it becomes low. You can learn a 555 IC operating.
Here we are using positive edge triggered D-type flip-flop, which means the flip-flop only responds when clock pulse would go from low to high. Output Q will be shown according to the state of the input D at the time of the clock pulse transition from low to high. The flip-flop remembers this output state Q either high to low until the next clock pulse low to high, and again shows output Q according to the input state D at the time of the clock pulse transition from low to high. Here the D-type flip-flop is basically advanced version of the SR flip-flop. In SR flip-flop, the S equal to 0 and R equal to 0 is forbidden because it makes the flip-flop behaving unexpectedly. This problem is resolved by using a D-type flip-flop by adding an inverter between both the inputs, and the second input is given the clock pulse to both of the NAND gates. Inverter is introduced to avoid some logic levels at both the inputs so that S equal to 0 and R equal to 0 condition never occurs. D-type flip-flop does not change its state while clock pulse is low because it gives the output clock at logic level 1 at NAND gates A1.
And when both the inputs are 1 for NAND gates X and Y, then outputs does not change. The conclusion is that it will not change its states when clock pulse is low, regardless of input D. It only changes when there is transition in clock pulse from low to high. It want to change during the high and low period. We can reduce the truth table for the D